So now we're going to flick over to the energy side of the app. So you can do that down the bottom here. Intro systems energy is the last one. What we're going to do is we're going to turn on the force plot and all of these little toggles. Actually, I don't know if we need the displacement arrow. So that'll tell us exactly sort of what's going on for this spring. So if we set our spring constant to 200 and our displacement, we'll set it as 250, 0.25, sorry, meters. That'll give us the same scenario that we were looking at earlier. So this is a graph of Hooke's law. And as you know, Hooke's law should give you a straight line going right through the origin. The gradient of this line, how steep it is your spring constant. So notice, if I increase my spring constant here, the gradient increases, and if I decreases, the gradient decreases, but we'll keep it on 200 for now. And if I increase and decrease the extension, I just move along that line. So if we look at the potential energy sides of things, every time I either shrink, compress, or extend this spring, it'll want to snap back to where it was originally. So if I make it really long, it just wants to squeeze back to its original size. So you can see it's got a massive potential energy here of 100 joules. That means that if I let go of that spring, it will snap back. And the same thing happens if I compress it. If I compress it with 200 newtons of force, the potential energy is 100, and it really wants to snap back to its original size where this green line is. So that's why we call it elastic potential energy, because that's what it would do if we let go. It's also the work done to the spring. So if I compress the spring, I compress it by 1 meter and I apply a 200 Newton force, I've had to do 100 joules of energy to do that. So you can view it as the potential energy stored by the spring, and you can also view it as the work. And it's important that you recognise work done is a format of energy as well. So, if we were to look at this, one thing to notice is that this graph is the force applied with the displacement x. We know that the gradient of the line is the spring constant, but in physics we quite often find ourselves finding the area under the line. But what is that area and what does it represent? Well, it turns out, you can figure this out by clicking the button over the side here. It turns out that that sort of blue area is the energy that was applied to the spring, or the work done, or the energy stored by the spring. And so we can use our maths of finding the area of a triangle to find out what that is. So if for now we turn off the values and we have a little look at what's going on. So this is F, this is my force axis, and this is X, my displacement axis, and this is a triangle which represents the energy. So I know that the energy E of this spring is going to equal the area of the triangle, which is a half times the base times the height. But in this case, it's going to be 1/2, but going upwards, I got my force, which is F. And then going across, I got my displacement, which is X. And so I know that the energy of my spring is going to be 1/2 times the force times by its displacement. So I can write that explicitly as the work done in squishing a spring or extending a spring, or the potential energy stored by the spring, is equal to 1/2 times the force applied times by the extension. Super important. Work done is 1/2 times the force times the extension. And you need to understand that this comes from finding the area of this shape. So now that you know that, We're going to use the app in the next few questions to see if we can figure out some problems with it.